So we are now going to see another examples of consistency. So if y is a number of success in n Bernoulli trials, then y by n is a consistent estimator of p, and y by n bracket square is a consistent estimator of p square, and y into y minus 1 divided by n into n minus 1 is a consistent estimator of p square. So we have to check all these, whether these are consistent and how they are consistent. So to check that, we will consider first. So here y is the number of success in n Bernoulli trials. So y follows binomial np. So expected value of y is equal to np. So expected value of y upon n is equal to n. So expectation of y upon n is p. So first condition, sufficient condition is satisfied. Now consider variance of y. So it is n into p into 1 minus p. npq, that is q is 1 minus p. So 1 upon n into p into 1 minus p. So variance of y upon n is equal to 1 upon n square into variance of y, and which is nothing but n into p into 1 minus p divided by n square, and which is equal to p into 1 minus p divided by n. And this tends to 0 as n tends to infinity. So both sufficient conditions are satisfied. So y by n is a consistent estimator of p. Now as y is y by n is a consistent estimator of p, therefore by invariance property of consistent estimator, we have, if Tn is a consistent estimator of theta, then phi Tn is a consistent estimator of phi theta. So here phi Tn is a consistent estimator of phi theta, where phi is any continuous function. So y by n bracket square is a consistent estimator of p square. So since y by n is a consistent estimator of p, so this is a y by n function. So this is proof, another proof. Now we will consider y into y minus 1 upon n into n minus 1. So this can be written as, now we will see how it can be written, y by n into y upon n minus 1 minus 1 upon n minus 1. So this is equal to y by n. So y upon n minus 1. So this can be written as an into y. So this can be written as n upon n minus 1 into y upon n. So we required y upon n here, minus 1 upon n minus 1. So this is equal to y by n, and this is an tn. So tn may be considered as, so here an tn minus bn, where tn is y by n, an is n upon n minus 1, and bn is 1 upon n minus 1. So an is equal to 1 upon 1 minus 1 upon n. This will tends to 1 as n tends to infinity. Since this is 0, 1 upon 0 is 1 upon 1 minus 0 is 1 upon 1 and 1. So consider bn, 1 upon n minus 1. This tends to 0 as n tends to infinity. And so therefore an tn plus bn is a consistent estimator of P. Since Tn is a consistent estimator of P. So this is because of we have a theorem or result. If Tn is consistent estimator of P, then An Tn plus Bn is consistent estimator of P, where or if Tn is consistent estimator of theta, then An Tn plus Bn is consistent estimator of theta, provided An tends to 1 and Bn tends to 0 as N tends to infinity. So here these conditions get satisfied, An tends to 1 and Bn tends to 0. So this is consistent estimator of P. So this is equal to Tn into An Tn minus Bn, or it can be taken as my plus Bn minus Bn. So this is equal to, this also tends to P into P, that is P square. So this is a consistent estimator of P square. Since this is consistent estimator of P and this is also consistent estimator of P, so P into P, that is P square. So this is a consistent estimator of P square. Now we will move to another example. Suppose we know that suppose x1, x2, xn is a random sample from population with mean mu and variance sigma square. Then we have to show that small s square is biased estimator of sigma square and it is consistent estimator of sigma square. So this is a consistent estimator of sigma square, and we have to show capital S square is unbiased estimator of sigma square, and it is also consistent estimator of sigma square. Consistent estimator of sigma square. So this we have to show. Now we will show it. Now to show this, we know that expected value of small s square is n minus 1 upon n into sigma square. We have derived it in my previous lecture, or refer to examples on unbiased estimator. In that video, I have shown that expected value of small s square is n minus 1 upon n into sigma square, and expected value of capital S square is sigma square. So this is not this is biased and this is unbiased. So consider bias of S square and sigma square. So n minus 1 upon n into sigma square minus sigma square. So this can be written as sigma square, take outside, n minus 1 minus n divided by n, and this is minus sigma square upon n. So this tends to 0 as n tends to infinity. So bias tends to 0 as n tends to infinity. First condition gets satisfied, and here it is unbiased, so bias is already 0. Now we will use one result by weak law of large number. Weak law of large number. We have 1 upon n summation xi square xi raised to r is a consistent estimator of expected value of x raised to r. By weak law of large number, we have this result: 1 upon n summation xi raised to r is a consistent estimator of expected value of xi raised to r, x raised to r. So we will use this theorem. So what is a small s square? Small s square is 1 upon n summation xi minus x bar bracket square. This can be written as summation xi square upon n minus summation xi upon n bracket square. This is summation xi square upon n minus x bar square. So by using this result, what we have? 1 upon n summation xi square is a consistent estimated of expected value of x square, and 1 upon n summation xi is a consistent estimator of expected value of x. We have known that the sample mean is consistent estimator of population mean, and this is we have. So by vehicle of large number, we have this result. So s square is equal to summation xi square upon n minus summation xi upon n bracket square is consistent estimator of expected value of x square minus expected value of x bracket square, and this is variance. So this is a consistent estimator of variance, but this is not unbiased. This is biased and negatively biased. Now s square is 1 upon n minus 1 into summation of xi minus x bar square. So this is n upon n minus 1 into s square. So s square is nothing but n upon n minus 1 into s square. So this can be written as 1 upon 1 minus 1 upon n into s square. So this is a form an tn, where tn is small s square. So an, which is equal to 1 upon 1 minus 1 upon n, this tends to 1 as n tends to infinity, and tn, that is s square, is a consistent estimator of sigma square. So by using result, an tn plus bn is a consistent estimator of theta. If tn is a consistent estimator of theta, by using this result, what we have? So capital S square, that is s square into n upon n minus 1. This is a consistent estimator of sigma square. Since this an tends to 1 and this is consistent estimator of sigma square, we have proved. So this is result. That is, small s square and capital S square are both consistent estimator of sigma square. So this we have. Now we will take another example, and suppose x1 x2 xn is a random sample from uniform 0 theta. So it is a random sample from uniform 0 theta. Then we have to prove that. Then we have to check. Then we have to show that Tn is equal to product of xi raised to 1 upon n is consistent estimator of theta upon e. So this is a consistent estimator of theta upon e. So what we have? We have to check its expectation and its variance, and then we can prove it. So consider expected value of Tn, that is expected value of product xi raised to 1 upon n. So product xi raised to 1 upon n. So which is nothing but expected value of x1 raised to 1 upon n, x2 raised to 1 upon n, xn raised to 1 upon n. So this is equal to expected value of x1 raised to 1 upon n up to expected value of xn raised to 1 upon n. This is possible since x1, x2, xn is a random sample, that is, they are independent. So we have this. So product of expected value of xi raised to 1 upon n. Now we have to find this expected value of xi raised to 1 upon n. So we will now find expected value of xi raised. So expected value of xi raised to 1 upon n. Expected value of x raised to 1 upon n, where x is a uniform 0 theta. So this is equal to 0 to theta x raised to 1 upon n upon 1 upon theta dx, x raised to 1 upon n. So this is nothing but x raised to 1 upon n plus 1 divided by 1 upon n plus 1, 0 to theta into 1 upon theta. So this is equal to theta raised to n plus 1 upon n divided by n plus 1 upon n into 1 upon theta. So this is equal to theta raised to n plus 1 upon n minus 1 into n upon n plus 1. So this is nothing but theta raised to n gets cancelled, so theta raised to 1 upon n into n upon n plus 1. By taking LCM, n minus n plus 1 divided by n, that is theta raised to 1 upon n. This is expectation. So now consider expected value of product of xi raised to 1 upon n, and this is nothing but product of expected value of xi raised to 1 upon n. So this is nothing but product of theta raised to 1 upon n into n upon n plus 1, this product. So what we have? So this is a product of constant term. So this can be written as theta raised to 1 upon n raised to n into n upon n plus 1 raised to n, and this is equal to theta into n upon n plus 1 raised to n. So this is bias estimator, and so this is bias estimator. Now we will take limit as n tends to infinity. So now we take its limit. So before taking limits, we will simplify it as 1 upon theta upon 1 upon 1 upon n raised to n. So this is this simplification. So limit as theta upon 1 upon 1 upon 1 plus n raised to n, and this limit is theta upon limit of 1 upon 1 plus 1 upon n raised to n as n tends to infinity. This is E. So this is unbiased estimator of theta upon E as n tends to infinity. So now we will consider its variance. So Tn is product of xi raised to 1 upon n. So variance of Tn is equal to expected value of Tn square minus expected value of Tn bracket square. So expected value of Tn square. So expected value of Tn square, that is expected value of product of xi raised to 2 upon n minus expected value of Tn, that is expected value of Tn, that is expected value of Tn bracket square. We have derived expected value of Tn. So consider expected value of product of xi raised to 2 upon n. This is the typical expected value of product of expected value of xi raised to 2 upon n. So now we will calculate this expected value of xi raised to 2 upon n. So expected value of x raised to 2 upon n, integration 0 to theta 1 upon theta x raised to 2 upon theta dx. So this is nothing but 1 upon theta x raised to 2 by n plus 1 divided by 2 by n plus 1. So this can be written as 1 upon n plus 2 upon n. This is, we take LCM. So theta raised to 2 plus n upon n minus 1. This theta goes upside, so this is theta raised to minus 1. So this can be written as n upon n by 2 into theta raised to 2 upon n. So this is expected value of x raised to 2 upon n. So now we will take product of n upon n plus 2 into theta raised to 2 upon n. So this can be written as n upon n plus 2 raised to n into theta raised to 2 by n raised to n, and this is this can be written as theta square. So n upon n plus 2 raised to n into theta square, that is its expected value of xi tn square. So we have both expected value of tn and expected value of tn square. So now we can find variance. To find variance, we have to find expected value of tn, and what is expected value of tn? We have derived it as n upon n plus 1 into theta raised to 1 upon n, that is expected value of xi raised to 1 upon n. So this can be written as expected value of this is equal to, so variance of tn is equal to n upon n plus 2 raised to n into theta square minus to n into theta, and we have to square it. So we can take outside theta square. So this can be written as variance of tn, so theta square into n upon n plus 2 raised to n minus n upon n plus 1 raised to 2n. So we have to take limit of variance of tn. Limit as n tends to infinity, variance of tn is equal to limit as n tends to infinity. Theta square can be taken outside the limit, so this can be written as 1 upon 2 upon n raised to n minus 1 upon 1 plus n raised to 2 upon n. So theta square into limit of this is 1 upon e square, and limit of this also is 1 upon e square, and this is theta square into 0. So this is 0. So variance of tn tends to 0, and expected value of tn is theta upon e. So product of xi raised to 1 upon n is a consistent estimator of theta upon e. So this is an example which shows the product of xi raised to 1 upon n is a consistent estimator of theta upon e. Thank you.